Good morning, evening, or afternoon, wherever you are in the world. My name is Katie Skillington, and today it's my pleasure to virtually present this paper, Design for Dematerialisation, an approach for reducing a building's embodied environmental flows. We're all aware that building operation and construction contributes to significant environmental degradation. And as a result, the sector is under pressure to rapidly adopt more environmentally sensitive practices in creating the spaces in which we live, work, and dwell. To date, most efforts in doing this have disproportionately focused on the effects arising from building operation, which overlooks the increasingly significant embodied environmental flows such as water, energy, and greenhouse gas emissions. These initial and recurrent embodied effects are often locked in during the building design phase, with a spike in demand or emissions occurring at building construction. With building operational efficiencies continually being improved and regulated for, and net zero and nearly zero energy buildings becoming more commonplace, a trend of embodied flows outweighing operational flows has emerged. Amplified by a continuing demand for construction material and resources due to population and building area growth, the need to address embodied environmental flows has never been more important. So who is well placed to address this challenge? Stakeholders who determine a building's construction assemblies, materiality, and finishes, so designers. To do this though, we need to support our design stakeholders with improved information on design approaches that target a building's materiality and their possible effect on embodied environmental flows. Design for Dematerialisation, which is concerned with the reduction of material and resource inputs, is one approach that warrants further exploration due to its hypothesised potential. But it is currently not widely discussed in the building sector. This study sought to start to change this by providing the beginnings of this understanding, both conceptually and operationally. Conceptually, as an approach, dematerialisation is more commonly researched and applied in the fields of industrial ecology, product design, and manufacturing. By using these sources and the limited literature in the building and construction field, this study defines design for dematerialisation as an early-stage design approach that prioritises reduced material and resource inputs across all life cycle stages of a building, whilst not negatively affecting the building's operational performance or intended function. Although dematerialisation bears strong similarities to principles of other concepts, when reviewing the literature, one point of difference emerged. Dematerialisation is not solely concerned with incremental efficiency improvements or material substitutions within existing product systems or designs. Whilst efficiencies and substitutions may contribute to progress, efficiencies alone will not ameliorate the effects of the forecast increase in demand for resources, nor will any material substitutions that don't account for indirect impacts. Instead, dematerialisation requires a fundamental rethink or redesign of the product system from project inception, employing a life cycle perspective so that all indirect and direct impacts are considered and addressed from early on. To form an operational understanding of the approach, some broad guidelines and actions were deduced from existing literature. Firstly, beyond the adoption of a life cycle perspective, Brown and Lutz-Carrillo suggest applications of dematerialisation should be guided by a tripartite strategy, starting with evaluating the necessity of components or functions, then determining which aspects are obsolete, and finally reducing and optimising what remains. Implicit in these guidelines is a questioning of user needs during early stage or pre-design work, and experimentation with alternative modes of delivering on these needs. Beyond these guidelines, there are also some broad actions that were determined as being part of the design for dematerialisation approach. Reduction via optimisation, which is probably the most obvious, includes reducing overspecification in structural systems, lightweighting, building system or construction assembly simplification, low energy, carbon, water intense products, or just simply getting rid of materials that are superfluous to servicing basic user need. Next, more intensive use, it was determined that this may involve reducing the physical footprint or size of a building, incorporating shared functions, or designing for multifunctional spaces and ongoing adaptability. Service life extension sounds pretty straightforward, and that's supported by the specification of more durable materials that require less frequent replacement or refurbishment, or designing for a longer building service life as a whole. And finally, reuse, recycling and repair, which can occur across multiple scales. So it could include something as big as the adaptive reuse of an entire building structure, the reuse of a small component, or the use of recycled construction waste in the creation of a new product. Now, although dematerialisation research in the building sector was found to be not extensive, several drivers and barriers can be inferred from other fields. So the primary driver for dematerialisation that was identified was often cost, and the desire to lower a product's production cost by reducing material inputs. Now, considering that cost is often cited as a barrier to the adoption of many environmentally sustainable design and construction practices in the building sector, this may position dematerialisation as an accessible, comparatively lower cost option for improving the environmental performance of buildings. Dematerialisation may also be driven by personal values, such as wanting to demonstrate pro-environmental values or behaviours in a physical way. Conversely, personal values may also be a barrier to the approach, as conceptually, dematerialisation is fundamentally opposed to the norm of consumption and some individuals' desirability of high consumption lifestyles. When we consider that ornament or architectural embellishment has been a way of personally expressing status, power, or wealth for centuries, the conscious act of reducing such elements through dematerialisation may be resisted by those who demonstrate wealth and status through their physical environments. Aesthetics presents another possible barrier, as the application of some design for dematerialisation actions, particularly in building interiors, results in a clear kind of industrial style that may conflict with the aesthetic preferences of some developers, architects, or even building occupants, which may in turn hinder the prevalence of its application. Finally, beyond conceptual and operational understandings of the approach, recommendations could be ascertained from the literature to further progress it, and these recommendations included the regulation of embodied environmental flows and the assessment of dematerialisation's effect on building performance. Now, few places in the world have measures in place for regulating embodied environmental flows or impacts. Yet, if measures such as targets or caps to the embodied environmental flows of a building were implemented, or more broadly to various economic sectors, a stronger impetus to pursue approaches such as dematerialisation would exist, and then likely result in increased use. Increased use would then lead to evolution of the approach, as its performance and outcomes would be heavily scrutinised in an iterative fashion, and experimentation will probably be more readily entered into. Progress of dematerialisation would be further improved if another gap was resolved, that being the lack of data regarding the effect of dematerialisation. Several dematerialisation actions have demonstrated independently that they can contribute to savings in embodied environmental flows. So, for example, increases in house size has been associated with increases in embodied environmental flows. Service life extension of a building can positively affect embodied energy demand, as studies have shown. However, there remains very little empirical evidence of the magnitude of effect these actions can have collectively in comparison to typical practice, and then the possible trade-offs that may occur. One-for-one reductions in material demand don't necessarily equate to equivalent reductions in an embodied flow. For example, a micro-apartment may lower floor area per capita and result in lower embodied energy and emissions. However, if that apartment is located in a tall building, these savings may be offset by additional structural requirements. Multi-criteria whole life cycle assessments of dematerialisation may help clarify the reductions in embodied environmental flows that can be reasonably achieved. It may also balance performance outcomes across multiple life cycle stages and uncover indications of possible negative second order or rebound effects occurring. So at a high level, the beginnings of understanding what dematerialisation is and entails in the building sector has been explored in this presentation and is summarised here. However, despite this further understanding, the question of by how much are embodied environmental flows affected by dematerialisation in the context of buildings' whole life cycle remains unanswered. Comparative multi-criteria assessments will help to demonstrate the relative performance of a building demonstrating dematerialisation, and more broadly, to better understand the approach itself. Once completed, we will more confidently understand whether or not dematerialisation holds promise in the building sector as a means to reduce the embodied environmental flows of a building and contribute to a reimagining of a more sustainable built environment. Thank you very much.